Zapata-Marin, who are going to talk about air allergens just in the city of Toronto, because Toronto is the most special place in the world, apparently. Dr. Lavigne comes from us, PhD at Laval, master's at Laval, but he's originally from Ottawa, and he's an adjunct professor at University of Ottawa. His main day job is with Health Canada, where he's a senior epidemiologist. Sara is a PhD candidate in her third year at McGill, an outstanding university in a wonderful city. So we're super happy to have her come join us here as well. I'll pass it over to them, and we can hear all about air allergens in the city of Toronto and how they vary spatially and temporally, which is one of our favorite topics. So please, looking forward to a great presentation.
Fantastic. Thank you very much for having us. Perhaps we can move to the next slide, please. Excellent. So just before we go into any of the specifics of today's I think this project is a very, very nice collaboration between different people of different expertise. And I have to say that this project came up several years ago, probably in 2016, when myself and my colleague, who's now professor at McGill, Scott Weikenthal, who we published a few studies on the effects of aeroallergen and health outcomes, and we thought that it might be interesting to perhaps create sort of a surface of aeroallergens throughout a city, because most studies only use one monitor per city. And so therefore, this is sort of how the idea came up, and I ended up partnering with Dr. Tim Taccaro and Jeff Brook, who were instrumental in the early stage of this monitoring work and putting forward the sort of identifying sites and trying to figure out how many sites we need and so on. And then came in Sara and her supervisor, Alexandra, because of the very complex spatiotemporal aspect of this study. Biostatistically speaking, it's a very complex analysis, and Sara will provide details today about this. And obviously, the at the bottom here, it's written Aerobiology Research Laboratory. We've partnered with them over several years, even before I was involved doing aeroallergen work, because they have monitors throughout Canada. They're a private company, and they have data on aeroallergens. So we partnered with them in order to have those monitors placed throughout the city of Toronto in 2018. And finally, my colleagues at Health Canada and also the AIR program that provided funding for the monitoring work for this study, which I'm very, very grateful for. So next slide, please. This is the overall agenda of today's presentation. Next slide, please. So like I said, the studies that were done on looking at how aeroallergens affect the risk of exacerbation to allergic rhinitis and asthma has been well studied over probably the past 20 years. Many studies across the world, including studies done in Canada. There's been quite a number of great papers that were published by colleagues from Health Canada, Dr. Bob Dales and Dr. Sabit Kakmak, who have investigated the associations between aeroallergens, how it fluctuates on a daily basis, and how it may affect the likelihood of hospital admissions or emergency room visits for asthma and allergic rhinitis. And there's more and more data that are coming today suggesting that there might be an evidence of early life exposure or infancy exposure to aeroallergens throughout several years, not just the short-term effects, but the longer-term effects on perhaps later lung function development. And there seems to be sort of a potential association between longer-term exposure and some development of atopic diseases like asthma and allergic rhinitis. Next slide, please. So we know that in a context of climate change, and this is partly why also we thought about doing this study, higher CO2 emissions, warmer temperatures will likely affect the growth and the pollen production in different plants. And I'm referring here to partly to a paper that was published in one of the collaborator who was mentioned on the acknowledgement page, Daniel Katz. And Daniel has been very helpful in the sort of plant ecology side of things in this project. And we know that increases in greenhouse gas emissions seem to be associated with higher allergenicity of pollen. There seems to be also warmer temperatures will likely lengthen pollen season, in the sense that pollen season might start earlier and end later in the year. There's also some data showing that CO2 emissions might actually produce more pollen. So this is sort of a pathway that's shown here on how the increase in CO2 emissions might actually increase the exposure to pollen, and in the end, increase exacerbation to allergies who are allergic to pollen. Next slide, please. So, like I said earlier, there's studies that were done looking at the effect of pollen on health outcomes, but most studies have investigated this issue through exposure for one monitor per city, in the sense that, for example, if there's one monitor in a city, well, if we're looking at the daily fluctuations, anyone that lives within that city will be sort of assigned the exposure to the levels that are being captured at that one single monitor. So, of course, for those who are familiar with the sort of air pollution epidemiology and all the exposure assessment side of things, we know that this may be sort of misleading because it may not capture appropriately the true exposure. And therefore, there's past few years studies that were done looking at how pollen might actually be spatially distributed throughout a city. Really nice paper that was done by Kate Weinberger in New York City. We're looking at intra-urban variation in tree pollen. And there was also an effort to look at how grass pollen varies throughout the Helsinki area in Finland. So those are among the very few papers that actually looked at the issue of the spatial distribution of pollen within a city. And one thing is that EPI studies using single pollen station as a proxy for pollen concentration are prone to significant measurement error, especially if the study area is climatically variable. So what we thought about is that there needs to be further evidence on the spatio and temporal variation. So not only how pollen varies within a city, but how it varies within a city over a certain amount of time. And this is sort of how we came up with the idea of conducting this study throughout Toronto. So on this note, I will let Sara present the next few slides and her analysis. I have to say that I'm really grateful that Sara was involved on this project, because she brought a very nice expertise in biostatistics, and you'll understand sort of why the complexity of the analysis. So Sara, it's your turn.
Thank you very much. Okay, so now I will start talking about the data that we have. So we have daily and weekly measurements of pollen concentration for 18 sites in Toronto from the Aerobiology Research Laboratory Monitoring Campaign in 2018. And the data goes from mid-March to mid-October. So we have data on different types of pollen. So we have grass, wheat, and 3 pollen, and we can also have the total pollen, which is just the sum of those 3 types. And then for 11 locations, the measurements were taken on a daily basis, and those are the locations shown in red. And for the remaining 7 locations, the measurements were taken on a weekly basis, and those are the locations shown in black. So from here on, I will refer to those sites as the daily sites and the weekly sites, respectively. So, for example, for the daily sites, we can have the weekly mean concentration by just taking the average over the days for those weeks. And then we also have some covariates. So we have urban land use factors such as commercial roads and buildings land use, and some environmental variables such as humidity, precipitation, and wind speed. But I will talk more deeply about the covariates in the next few slides. And then, okay, this was supposed to be moving, but so this is just a small, well, there are 2 bubble maps that were showing how the pollen concentration was changing across the city. So in the first map, it is for all the 18 sites, the weekly concentration for all 18 sites, and the second one is showing how the daily concentration for just the 11 sites. So, I mean, here, for example, for day 1, you can also see that we have some missing values in both the daily and the weekly data, but the way that we are modeling them, they are just parameters that need to be estimated. But even, for example, here in week 1, you can see how there is a greater pollen concentration for some of the sites, and then there is a smaller pollen concentration on other sites. Okay, and now this is a time series showing how the pollen concentration was changing for all the sampling period for one of the sites, one of the daily sites. So, for example, here in the upper panel, I am showing you the tree pollen and the total pollen, and on the lower panel, I'm showing you the spores and the wheat pollen. We also have some data on the spores, but I won't be talking about that. I will be focusing in the upper panel. You can see that the trees are can you hear me?
We just lost you for a second there. Or I think we've lost you again. Sarah, can you hear us?
Can you hear me?
Yes.
Yeah.
I think we have lost Sarah, which is unfortunate. We'll just give her a second to reconnect. There we go. You're back. Well, that's not good. Well, just give her a minute and we can try to reconnect. Because she did have a pretty stable connection until something happened. So
yeah.
While we're waiting, I just want to remind people that if you do have questions or comments, or you want to just have a stimulated discussion, please do use the chat. For many people, the chat should be almost at the top, almost dead center. It's under conversation, so there is a chat function there. Clearly, some people have found it, but yeah, if you do have comments or questions as we go, and the questions can be raised at the end. And here's Sarah coming back. So,
So Sarah, maybe a suggestion is perhaps to turn your video off.
I am having troubles. Apparently, like the internet just went off. I'm sorry. Let me try again then. Are you able to see my screen?
Yes.
Okay, I'm so sorry for that. Oh, well, now the GIFs are moving.
Oh, even better.
Exactly.
Life is good.
Okay, so again, now here you can see how the pollen concentration is changing across all the sites and for all the sampled season. So now here, again, I'm so sorry, but here in the upper panel, you can see that the total pollen is mostly the sum, well, it's showing mostly how the peaks of the tree pollen and the peaks in the weed pollen. So for example, trees bloom in early spring, grass blooms in spring and then during the summer, and then there is a peak in weed pollination at the end of the summer and the beginning of the fall. But there is something that that's interesting and that you can see from this time series is that there are a lot of zeros in the data because of how each of the different types of pollen are working. For example, in the grass pollen, you can see that at the beginning of the sampling season there were a lot of zeros, and then also by the end of the season. And we believe that that's something that should be accounted for. Okay, and now we also have some special predictors. So we have all roads, buildings, commercial, industrial, major roads, grass cover, tree cover, and bare ground land use. All of them we have them in as a proportion of 0 to 1 of land covered by any type of these different variables. And the source is from DMTI Special Inc., except for grass cover, tree cover, and bare ground that come from the City of Toronto 2018 tree canopy study. And then what we're calling the temporal predictors, we have TC greenness, which is the amount of photosynthetically active green vegetation with the different buffers for each month. And we have TC brightness, which is defined as a proportion from 0 to 1 of buffer covered by land use covered with albedo. And we have this data also for each month. And this data comes from Landsat 8 satellite images with high resolution. And then we have humidity, precipitation, temperature, and wind speed. So for humidity, we have the mean humidity within a day or a week in percentage. For precipitation, we have the precipitation level within a day or a week in millimeters. For temperature, we have the mean temperature within a day or a week in degrees Celsius. And for wind speed, we have average wind speed within a day or a week in kilometers per hour. And this data comes from Environment Canada. So it's important to note here that we have the data from one monitoring station, so we are assuming that the climatic variables are the same for all the 18 sites. Okay, and then for this project, there are three main objectives. The first one is to account for the high number of zeros that I showed you in the time series that you saw. So because of the seasonality, that might be stretching the term, but because of the seasonality of each type of pollen, we need to account for the high number of zeros in the data. And then the second objective is the temporal misalignment. So this is referring to the fact that we have weekly sites and daily sites. So we wanted to propose a model that would account for the fact that there are weekly and daily measurements. And finally, one of the other objectives is a multivariate model. So to propose a model that accounts for possible correlation between the pollen types. But today I will be just talking about the first and the second objective. So let's start with the model to account for the high number of zeros. So in order to account for the high number of zeros, we propose something that is called the Hordel model. So in this case, it's a Hordel log normal model. So if you know about zero-inflated models, this is really similar. But this is a mixture of a Bernoulli distribution and a log normal distribution. So here we are modeling the pollen concentration at week T and location S. So the pollen concentration at week T and location S is equal to 0 with this probability, and it's greater than 0 with a probability 1 minus rho. And if it's greater than 0, then the positive values follow a normal distribution with parameters mu T of S and sigma square. And the way that we model the mean for that model is that we have a vector that contains all the spatial covariates. So for this model, we are using the coordinates. So easting, northing, bare ground, commercial, industrial, major roads, grass cover, and tree cover. We have a vector that contains the climatic factors, precipitation, temperature, and humidity. We also have a vector that contains the brightness and the greenness for each site S at each week T. And then we have theta T. Theta T is a time-varying mean that captures the weekly overall temporal mean across sites, and it follows an equation that it's modeled like a random walk. So what theta T is doing is that it's capturing what is left after we account for the temporal covariates and the spatial covariates and the TC brightness and TC greenness, and it's capturing how the pollen concentration is changing across weeks in this case, but for all the city. And you will see how it looks in a couple of slides. Okay, and now if you remember, this probability can be modeled in different ways. So we tested 4 different models. In the first one, we are assuming that the probability that the pollen concentration is equal to 0 is the same for all weeks. Then in model 2, we are modeling that probability as a function of the week. In model 3, we are modeling the probability as the same way that we model theta T, so that it's a random walk, and what this means is that the probability that the pollen concentration is equal to 0 at week T depends only on the probability on the previous week. And then on model 4, we are modeling this probability as a function of the same climatic covariates. And then after we tested with WAIC and LU, we see that for grass and tree pollen, the best model was model 3, so that the probability depends only on the probability on the previous week. And for wheat and total pollen, the best model is model 4, so that the probability depends on the climatic covariates. And after we fitted our model, these are our results for each type of pollen. So for example, for grass pollen, we see that there is a positive relationship if the site is east of Toronto. There is a positive relationship with an increase of brightness, and a negative relationship with if the site is north of Toronto. And also, sorry, I don't know if I mentioned this, but there's a positive relationship association in the presence of industrial areas. And then for the total pollen, there is a positive association again with the industrial areas and with an increase of TC brightness. And for the tree pollen, there is a negative association in the presence of, with grass cover, and a positive association with commercial areas. And then for wheat, there is a positive association with industrial areas and TC brightness, and a negative association if the site is north of Toronto. So this is interesting because actually in some papers they mention that higher CO2 levels can increase the production of pollen in some plants. So this might be like this positive association with industrial areas might be showing that for wheat and for grass. And the total pollen is just because it's a sum of all the other pollen types. And now these are our estimates for the, on the left, these are our estimates for the climatic variables. So for example, for grass, we see that there is a positive association with temperature, also for the total pollen, and that's it. And this is also interesting because, for example, here we see that the pollen concentration, the tree pollen concentration is not associated with any of the climatic variables. And this might be because the amount of pollen that trees produce depends on the climatic factors on the week before. And the timing when the trees release their pollen depends on the climatic factors on the current year. So in this case, it would be on 2018. So it's okay that we are, at least for the trees, that we are not seeing any association between the pollen concentration and the climatic factors. And then, if you remember, for the total and the with pollen model, the probability for the measurements being equal to 0 depends on the climatic factors too. So there is so this probability increases with a higher humidity, higher levels of precipitation, and increases in temperature. And for the wheat pollen, it has a positive relationship with humidity, the intercept, the precipitation, and the precipitation. And for example, for ragweed, there are some papers that mention that the peak concentrations are reached around noon in the absence of high winds or rain. So it makes sense that the probability of the measurements being equal to 0 is, that these climatic factors are positively related with that probability of the measurements being equal to 0. Okay, and now if you remember, in the first row is showing the state vector. This state vector is the theta t that I showed you. So this is the same for all the city, but this is capturing what like the temporal variation of each of the types of pollen after accounting for the covariates. So for example, here in the tree pollen, you can see that there is a peak around week 10 and then it drops. And then here in the lower panel, I'm showing you the probability of the measurements being equal to 0. So for example, for the tree pollen, this probability is really low for the first few weeks, and then it starts to increase for the last 10 weeks. And we can see here also in our state vector that the pollen concentration just drops for that period. And then for the grass pollen, we can see that there is a small quantity of pollen for the first few weeks, and then there are two peaks, one around week 15 and one around week 25. And then in the probability is higher for the first few weeks, and then we have just a couple of peaks around week 21 and week 30. And then for the wheat pollen, the pollen concentration is really low for the first weeks, and then we also have two smaller peaks around week 15 and week 21. And then the probability is really high for the first few weeks, and then it's lower for the last weeks. And then for the total pollen, you can see these two peaks. The first peak corresponds to an increase in tree pollen, and the second peak corresponds to an increase in wheat pollen. And then the probability, because we have less zeros for the total data, the probability is really low throughout the sampling period. Okay, and now this map is showing the predicted surface for the tree pollen concentration for the week of May 13th in 2018. So I have never been to Toronto, which is kind of funny, but so I don't know much about the geography of Toronto, but for example, here you can see that there is a low tree pollen concentration, and I think here there is like a small airport or what it looks like a small airport, and I believe that this is downtown Toronto. So correct me if I am wrong, but there is a higher pollen concentration in this area. And you can see that north of Toronto, there are smaller tree pollen concentrations. And then, I'm glad that this is working. Okay, so this is the predicted surface for the total pollen. So here on the left, I am showing you the state vector for the total pollen, and you can see how it is changing across weeks. And then on the map on the right is showing the predicted surface for the total pollen and you can see how it is changing across time. The red dots, by the way, are the monitoring sites that were placed there. So for example, here you can see how it is increasing how the total parent concentration is increasing for all Toronto. So you can see the first peak there, and you can see how it increases for the whole city, and then it drops, and then again in August it starts, well, yes, around August it starts increasing again, and there you can see the second peak from the width pollen. And by the way, sorry, this is all in the log scale because it's easy to visualize it that way. Okay, and now the temporal misalignment. So if you remember, the temporal misalignment is a problem that we have because some of the measurements were taken on a daily basis and some of the measurements were taken on a weekly basis. So here we are modeling the log of the daily total pollen concentration. I am just using the total pollen concentration for this model for now because it's the one that has less zeros. So we assume that the log of the pollen concentration follows a normal distribution like this. So here tau is the index for the day, and it goes from 1 to 7, and t is the index for the week. So these are the days. Yes, it's the days in week t. And this mean is defined differently than the other one because this is in the daily scale. But here, u t of tau is a vector that contains the environmental covariates or the temporal covariates. So it contains humidity, precipitation, and wind speed. And x is a vector that contains the coordinates and land use covariates such as all roads, buildings, commercial, industrial, and open spaces. And here again, we have our time varying mean component. And it's modeled the same way as with the weekly data, but in this case, it's in a daily temporal scale. Okay, so now based on conditional independence on the daily measurements, it follows that the weekly pollen concentration is just the sum over the daily measurements for the days in that week over 7 because it's the weekly mean, and this follows a normal distribution with mean mu t, where the mean is just the sum over the mean for the daily measurements for that week over 7. And now we are interested on and estimated what the unobserved daily values would have been at the weekly locations. So in order to do that, we assume conditional independence and we use the bivariate distribution of each of the daily measurements at site S and the weekly measurements. So this follows a bivariate normal distribution with this covariance matrix, and we can use this marginal distribution. This marginal distribution, what it's saying is what are these are the daily measurements given the weekly measurements. And remember that for this, well, for some of these sites, we just observed the weekly mean concentration. So if we use this marginal distribution, follows a normal distribution with this mean, and this mean just depends on the mean for the daily values, the observed weekly values, and the mean for the weekly values. So here in the mean for the daily values, we are borrowing strength from the data that we have from the daily sites. And we are using the information that we know from the weekly observations. And then here the variance is just a function of the variance for the daily values. Okay, this map is showing, these plots are showing just the fitted values for the daily observations at the daily sites. So the black lines are the fitted values, the red lines are the estimated missing values, and the blue dots are the observed daily values. The gray area is a 95% credible interval. So here you see for the total pattern, you can see the pattern that we saw on the state vector, but now it's for each site, and you can see that it changes, the scale changes for each of the sites. And for example, we are having troubles fitting some of these values, and it might be because these are zeros in the data. And then the upper panel is showing the unobserved daily values at the weekly sites, and the lower panel is showing the fitted weekly values. So these were observed, and again, in the lower panel, black is the fitted values, red is the estimated missing values in the weekly data, and the blue are the observed values. And on the upper panel, the blue line are the predicted daily values when the week was observed, and the yellow is when the week was missing. So even though these graphs doesn't look as smooth and nice as these ones, we are capturing the overall pattern that we also see when we actually observe the daily data. And then we wanted to compare how the coefficient estimates would change if we fit the same model with the same coverage, just using the 11 daily sites, when we use the data using the weekly data for all 18 sites, and with our temporal misalignment model using both daily and weekly sites. So here the dots are the posterior mean estimates, then the thicker line are the 90% credible interval, and the thinner line the 95% credible interval. So you can see that our position is better when we're using both daily and weekly data, and that we found more, well, some associations that we wouldn't have been able to if we just used the daily or the weekly data. So for example, there is a negative association in the presence of roads with higher humidity, with industrial areas if the site is north of Toronto, with open spaces, and then an increase with an increase of precipitation. And there is a positive association in the presence of buildings, commercial areas, if the site is east of Toronto, and with an increase on wind speed. So this is similar to the one that I showed you for the weekly data, but this is showing how this is a smaller surface than for the weekly data, but this is showing how the total pollen concentration was changing for that season across all Toronto. So I guess that the airport was here, and I believe this is like a crossroad. So you can see that, and I think this is also where a park is. So you can see how it is, how the total pollen concentration is changing across all the city, and how it changes across different sites in Toronto. Okay, and well, finally, we were able to propose a model that accounts for the complex structure of the data that allowed for the temporal correlation in the mean, so the time-varying mean component that I showed you, and using land use variables to accommodate local information of the measurements. We were able to propose a model to account for the temporal misalignment in the data. We estimated the unobserved daily measurements at the weekly sites, and we found different estimates for the fixed effects depending on the temporal scale. So this also means that you might be able to find different associations depending on the temporal scale that you're looking at. And then some ongoing work is that we have to propose a model that combines the misalignment model and at the same time accounts for the large number of zeros in the data. So this model that I showed you before, it's just for the total pollen, because as I said, we have a less number of zeros in that data. And then we also want to propose a model, a multivariate model, to account for possible correlation between different types of pollen, so that we will be able to model the different types of pollen together.
Thank you, Sarah, for this great overview. And what I can add to this is that how useful is that data going to be? Because why did we want to come up with this surface across Toronto for pollen? And as I mentioned earlier, it was something that hadn't been done well before, and the idea is to have this surface so that we can first, if we are interested, or if any others are interested, I know some that might be interested in using this data, but it's to look at the effects of pollen on health outcomes using perhaps cohort studies or health administrative data that are available within Toronto, in order to perhaps evaluate maybe longer term effects of pollen, and perhaps we can try to figure out ways where we can estimate retrospectively pollen concentrations, similar to what is done with air pollution epidemiology when we back extrapolate concentrations. And the idea is also that the effects of aeroallergens combined with air pollution and temperature are very important in the context of global climate change, and therefore having this data will likely help in understanding the interactions between those climatic and atmospheric variables. We are also interested in creating those spatiotemporal grid surfaces, but with specific taxa species of pollen. What we discussed today was the grass, trees, weeds, but with the data that was analyzed, we also have the specific types of trees, pollen levels. So it is something, it's possible to do this, because in the context of urban planning and greening of cities, there is really a need to better understand the spatiotemporal exposure to specific types of pollen. And are there specific types of pollen that are implicated in more exacerbation or development of atopic diseases? So we can work with urban planners in order to identify the specific types of pollen that may reduce exposure to allergic exacerbation. And one thing I want to say is, Sarah mentioned that this monitoring campaign was done because we had weekly measurements. So we had 7 sites where we had weekly measurements, and we had 11 sites that were measuring on a daily basis. And it was an enormous amount of work for those people who were involved, and that I want to thank the citizens that were involved, because people, mainly Toronto Public Health, was helpful in finding people who were interested in having a pollen sampler in their backyard, and had to change the pollen sample every day from mid-March to mid-October. Thank God there was no pandemic in that year, but they basically had to change the sampler every morning from 7 a.m. to 9 a.m. It was a time frame they had to change the sampling. And so I'm really, really thankful for those people who were involved. We even had at one point someone who moved and had to change address. So all to say that I'm really thankful for the citizen science involvement of this project. And on this note, I thank you all for listening to this presentation.
And I would also like to thank my sponsors, Amexit, Conacyt, my program, QLS, and Health Canada. Thank you.
Excellent. Thank you for a wonderful presentation and a huge amount of information. What I'm going to suggest is that there are already some questions on the chat. So why don't we start with a few of those, and then encourage others. If you have questions, once we've done some of those, you can either speak up with the microphone, you can put up your hand. There's a hand symbol on the top of the screen, or we'll figure something out. But Eric, can you see the chat?
Yeah, I can go and
Yeah,
I can see the chat. Yeah, absolutely. I can go maybe to some of the first questions.
Yeah, I think so.
Okay, so perhaps one question that might be, I don't want to defer all questions to you, Sarah, but I see one question is, can you clarify why the coefficient estimates for temperature has a greater deviation than humidity or precipitation?
Yeah, we are not sure about that, because at first we thought that there might have been like some correlation with the other variables, but there was not. So we are not sure why that's happening. But yeah, that's something that we have to check.
Okay, so I have a question from Keith on how were the measurement sites chosen. So I guess that might be more a question for me. And I have to say that initially I had to go through a sort of a random allocation of site and identifying areas within Toronto where we could put sites. And one difficulty that I had was that it's not like when we do air pollution studies, for those who are familiar, where we can either drive around a city, or we can with samplers on a car, or if we put samplers on posts. The samplers had to be in people's backyard, and people had to actually change the samplers every day or every week. So the idea was to find, initially I identified several areas within Toronto where samplers had to be available, and then it was also a matter of combining where people lived and those who were interested in participating. At one point, I remember I had to refuse a few potential participants because the samplers were basically going to be too close to each other. And so you can see here there are still samplers that are very close to each other. Obviously, it's related to some of the population density. As we get more southern part of Toronto, it gets more dense, and there's a bit more people that were available to do the sampling there. Perhaps the next question is, and I may differ to you, Sarah, could you reiterate the rationale for including the easting and northing coordinates as predictors?
Yes, we at first we wanted to see if there was some spatial structure in the data, but I tried for months and apparently there's no spatial structure in the data. But for those kind of models, then you use the coordinates so that might show. Yeah, so that might show some of the like spatial structure in the data by just knowing if it's east of Toronto or north of Toronto. But usually in spatial statistics, you also have an additional term here that will account for what is left after accounting for easting and northing.
Question from Céline. Did you consider pressure as a variable to track weather events? So, for example, thunderstorms, since many asthma occurrences happen before thunderstorm. So, are you able to answer this, Sarah?
Nope, because I mean we have just the precipitation, temperature, and humidity data, and wind speed too.
Yeah, so I think we had at one point pressure, atmospheric pressure in the data, the climatic data that we had. We ended up not using it. I don't remember the exact reason for it. We perhaps didn't think that it would be necessarily a strong predictor in order to capture the spatial prediction of pollen. But I mean, it's a good question, Sidin. I have to admit. So perhaps next question is also curious about inclusion of UTM values. I expect UTM is going to some of your other inputs like MET. Did you see covariance of UTM with other inputs?
Like the UTM coordinates, you mean?
Yeah.
So, I mean, that's why we're using the easting and the northing, we're using it in the UTM coordinates to account for that, but I'm not sure if I understand the question.
Taylor, do you want to rephrase your question?
I can elaborate on the question. I'm just wondering, because with your model, if you're using UTM coordinates as an input, you're going to see, for example, humidity will be associated with, like, a decrease in humidity will be associated with an increase in the northing, because the lake is on the south bound of your.
Yeah, but
you might see that with some other, and if, for example, you're using like proximity to industrial zones, if I'm understanding your X vector correctly, then if like industrial zones are clustered, so you're going to also see covariance between like the results based on easting and northing is going to also covary with those inputs as well.
Yeah, one of the things is that, for example, for the climatic coverage, that's not a problem. because we are assuming that the climatic covariates are the same for all the city, which might be wrong, but that's like that's the data that we were able to have. So, I mean, for the climatic factors, that wouldn't be a problem because we're assuming that they are the same for all the 18 sites. For the other covariates, there were no correlations between the coordinates and the other variables, but yeah, I see what you're saying. And also, for example, here easting and northing might be accounting for some other special covariates that were not measured or that we don't have data on, but that they are correlated with that easting and northing. So in that sense, that would be kind of beneficial to us.
Perhaps another question is how have you factored long-range transport of pollen?
I'm not sure I am able to answer that question, but
yeah, I think because long-range transport of pollen, we didn't look at this. We well, obviously the samplers were capturing pollen at the location, so we don't know if it's long range or short range pollen, although my understanding of the rotor rod samplers that were used, they're mainly they're sort of validated to capture in and around the pollen that's in and around the where the sampler is located. So I don't think the long-range transport would be a major issue in the samplers that we used.
So I think we're close to the hour. I'm going to just take one more question.
I'm not going to take the questions that towards the maybe there's one last question here. What future sampling are you planning, and what would that sampling strategy look like based on what you've found here? I don't have any new sampling ideas on the way, although I think that replicating the multi-site sampling within a city, I think would be interesting, whether it's within another Canadian city or elsewhere, because I think it would be interesting to compare sort of the predictors that we found, the spatiotemporal predictors that we found, and see if it might be consistent in other areas, whether the climate is similar or not.
Yeah. Well, thank you very much both for a fascinating presentation. I was intrigued by the spatial map for Toronto. I know some of the pitfalls of doing analysis of cities that one does not live in. And when you have an audience of people who do live in the city, I think one of the areas that you indicated had low amounts was up near Downsview. And then certainly there's a mix of things up there, including, it looks like Environment Canada was one of your sites. And I was going to make a joke about question if there's any intelligent life around in that area, but I'll leave that to my colleagues at Environment Canada to think about.
Well, I would say that was Jimmy Jiang that took over that job, weekly sampling changing for much of that summer.
Okay.
Well,
but it is interesting. The other thing it looked intriguing is that some of the maps we see for socioeconomic status seem to be sort of related to some of the maps that you showed. And just the idea, is there more a case of environmental justice here, in that some of the places of higher socioeconomic status actually seem to have the higher counts, which I think would be a nice little twist, because too often it's the other way around. But thank you both for a fascinating presentation. And I'll encourage any of the attendees today, if you didn't have your questions answered, please follow up with Eric and Sarah. It seems like the work is going to be ongoing. There's lots more to be discovered. So we look forward to hearing more as it progresses. And Sarah, every success in completing your PhD. So.
Thank you. I'll need it.
All right. Thank you all for joining us. And our next seminar is going to be in January. So have a great holiday to everyone.
thank you.
Thank you.
Thank you all.